Sketched below are the graphs of f of x, which equals to k over x plus q, and g of x, which equals to x plus 2. The equation of the horizontal asymptote of f is y is equal to 1. So that will be the q value that's here, right? The q value that lies here. And the graph of g cuts the x-axis at b. So that's the x-intercept of this graph G, of the linear graph. Graphs f and g intersect at a and b. Okay, so the value of q should be 1. Right, the value of q should be 1 because it's the horizontal asymptote. The domain of f, so the domain is a set of x values for which the function exists. Okay, so it's the set of x values for which the function exists. So we know that the function will exist for all values, all real values, right? So if you look at the number system, for all real values mean the number could be irrational, could be rational, and everything that falls within a rational number. So that is your natural, your whole numbers, and integers. So it can be any of these values, but it cannot equal to 0. And you can look at this in two perspectives. The reason it cannot equal to 0 is because x is the asymptote. The function will tend to the value, but it will not touch it. It will not touch the value. It will not become 0. And if you look at the standard form, in this case, the denominator cannot be 0. Remember, anything divided by 0 is undefined, right? So we can state the domain, right? We can say that the domain is x element of real, but x cannot equal to 0. Okay, so 5.2.1, the equation of the line of symmetry of f that has a negative gradient. So remember that when we drew the hyperbolic function, remember these functions are literally just always in relation to the parent function. It's always in relation to the parent function. So the parent function is a function that has no transformations and no translations. So in our case, the parent function would have looked such. So remember, the parent function has the equation y is equal to 1 over x. Now we also know that it has a line of symmetry that runs through the region, and it has the equation y is equal to x, and the negative line of symmetry will be y is equal to minus x. So what the line of symmetry is, right? This is the important part. What information does the line of symmetry give us? Now, as I explained in the previous video, that when we talk about reflection, so let's say that we have the Cartesian plane here, and I'm trying to reflect this point about the x-axis. If I try to reflect it about the x-axis, I need to do two things. I need to make sure that I reflect it such that it's perpendicular, so it's a vertical shift. It's a vertical shift, so it'll move along this value perpendicular to the line of symmetry. So in this case now, I'm going to reflect it about the x-axis, and it must shift by the same units in the opposite direction. So it has to shift by the same number of units in the opposite direction. So that would be at this point. Okay, so if this was 4 units, let's say, then it needs to shift in the negative y direction by minus 4 units. Okay, now likewise, we're doing the exact same thing with the line of symmetry. That's what the line of symmetry is. We are doing the exact same thing. However, since these lines are not perpendicular, they are at an angle. Now we have to make sure that when we're shifting, we shift perpendicular to the line of symmetry. So in this case, since we have the equation y is equal to x, if I have to draw a line perpendicular, it should look as such. Okay, it's perpendicular to the line of symmetry. Can you see that? And so if I'm shifting in the or reflecting about the line of symmetry, then this point here, when it's reflected about the line of symmetry, must be perpendicular to the line of symmetry and move by the same amount of units but in the opposite direction. So therefore, if this shifted 4 units up in whatever direction that is, then it needs to shift by 4 units in the opposite direction, and that's how we locate the point. And so if I do that for all of these points, if I do that for the point that lies adjacent to it and so on, I should yield the same curve on the opposite end. So if I have to isolate this, okay, if I have to isolate this, and if I have to isolate this function, so basically let me do this. Let me make this a green portion, make this the green portion, and make that the red portion. And if I do that for every point, eventually what I would end up with this becoming red. This curve here, this mini curve here from here to here, would eventually go across the line of symmetry, and this green curve would eventually come on the bottom portion. And so what the line of symmetry is, it's a line that after I reflect the graph, I yield the same graph. So the graph will still remain the same. If I reflect the graph, I will yield the same graph. So in the other case, so this is the line that we call the positive gradient. It's a line of symmetry of the hyperbolic function with the positive gradient. If I do the exact same thing with the negative gradient, you can imagine, remember that these graphs are the same. So you can imagine that this graph would eventually assume this shape, and this graph would eventually assume this shape. And so we understand that the hyperbolic function has two lines of symmetries, right? And so there's no change to the graph. The graph will look exactly the same before reflection and after reflection. Right, so knowing this now, remember that the parent function has these two lines of symmetry, y is equal to minus x and y is equal to x. They asked us for the negative gradient, so we focus on this line. Now, what happened to the function? Did the function not shift 1 unit up? So therefore, everything will shift 1 unit up. From the parent function, everything will shift 1 unit up. And so therefore, the line of symmetry of f that has a negative gradient should have the equation y is equal to minus x plus 1. Okay? The equation of f. Now, if we're trying to define the equation of f, we would need to find at least a point that lies on the curve. Remember, so far, we have this. So we just need to find a coordinate that lies on the curve, and we'll be able to find the value of k after substitution. So we know that b lies on the curve, right? And it so happens that b coincides with or rather lies on the graph of g, and it's the what? The x-intercept. It's the x-intercept of g. So therefore, what I can say, the x-intercept is the point where y is equal to 0, and so x plus 2 is equal to 0, so x is equal to minus 2. So therefore, that coordinate b is minus 2 and 0. So now I can substitute that into the equation. So 0 is equal to k over minus 2 plus 1. K is equal to minus 1. So k is equal to, that's minus 2 minus 2. K is equal to 2. And so therefore, the graph of f has the equation of 2 over x plus 1. Okay? Alright, so define the coordinates of A. Remember, A is the point where both the graphs intersect, right? In fact, it's one of the points where both the graphs intersect. B is the other point, right? So therefore, what we can say is that it's the point of intersection, so we can equate both the graphs. So 2 over x plus 1 is equal to x plus 2. We can conclude this because it's given that it's the point of intersection. Let's multiply by x throughout. So this will be x squared minus, so what does this become? Minus x becomes plus x minus 2 is equal to 0. And two numbers that when multiplied together gives me minus 2, but when added gives me plus 1. That numbers should be plus 2 and x minus 1. Okay. So x is equal to minus 2, x is equal to 1. This, in our case, this is not applicable because x has to be greater than 0. Remember, we're on the positive x-axis. A lies on the positive x-axis, so that's 1. So therefore, if I want to find the corresponding y value, I'll just have to input that into either of the functions. I will do that for the g function, and is equal to 3. So therefore, A has the coordinates 1 and 3. Okay. And so that's about it for this question. Okay, the graphs defined as g of x is equal to ax squared plus q and f of x is equal to k to the power of x minus 4, both pass through minus 2 and 0 on the x-axis. The y-intercept of g, which is the parabolic function, is 0 and minus 5. Okay, so 0 and minus 5. So what we can say now is that the value of q, since we're given the y-intercept of g, the value of q is equal to minus 5. Right? It's equal to minus 5 because remember the y-intercept and the turning point are represented by q, right? Because we're only talking about a vertical shift. So it's 6.1.1. Okay. So find the equation of the asymptote of f. So the asymptote of f is given by the q value. Okay. So therefore 6.1.1 will say that, okay, we can't say q in this case. Okay, so the equation of the asymptote of f is y is equal to minus 4. 6.1.2. The value of q, remember we just said that the value of q for the parabolic function represents both the turning point and the y-intercept because we only have a vertical shift. So therefore, we can say that q is equal to the y-intercept. They were given the information on that. So therefore, q is equal to minus 5. Now the coordinates of the other x-intercept of g. So how are we going to do that? Okay. So what we are given here is that if we just do a rough sketch, okay, that won't even be possible. But we say that both the graphs pass through this point, and this point here is the x-intercept. Now I think this question is very good because it teaches us about a few things, right? We know that the parabolic function has a turning point at minus 5, and we know that one of the intercepts is minus 2. Now remember we just discussed about the line of symmetry, and the line of symmetry of the parabolic function is the y-axis. It is the y-axis, right? So therefore we can say it's the y-axis, but more generally we can say it's the line that passes through the turning point. It's the x-coordinate of the turning point. Let's call it that, right? Because it'll be very useful when you come to grade 11. So line of symmetry, the line of symmetry, right, is given by the x-coordinate of the turning point. And in this case we notice quite a few things. Is that the x-coordinate of the turning point is actually the y-axis, because at the x-coordinate of the turning point is 0 and 5, so therefore it'll be x is equal to 0. So that's the equation of the line of symmetry. What do we know about the line of symmetry? Is that every point, see even this point here as well, every point must move. Now in this case it won't move vertically, but now it will move horizontally because the horizontal line is perpendicular, and it will move by the same distance. So it moves by the same distance. If this is minus 2 units to the left, this will be 2 units to the right. And so therefore I can locate the roots, the second root by 2 and 0. So therefore I can say that the other x-intercept of g will be given by 2 and 0 just by using the line of symmetry. Okay, you see the line of symmetry put to use there. Okay, so to find the equation of g of x, we write that g of x is equal to ax squared minus 5. Remember that I've already discussed that minus 5 is the turning point and the y-intercept of g. So now what I have to do is I can just substitute a point and I can solve for a. So we can say that I know the x-intercept is minus 2 and 0. So therefore 0 is equal to a into minus 2 all squared minus 5. Remember, whenever you make a substitution, you must parenthesize. So therefore 5 is equal to 4a. Therefore a is equal to 5 over 4. So therefore g of x has the equation 5 over 4 x squared minus 5. Okay, so now we have to solve for f of x. So we know that f of x is equal to k to the power of x minus 4. We know that it passes through the point minus 2 and 0. So we just have to substitute this point and solve for k. So 0 is equal to k to the power minus 2 minus 4. 4 is equal to k to the power minus 2. Then I can say that 4 is equal to 1 over k all squared. So find the square root of both sides. Be plus or minus 2 is equal to 1 over k. So therefore k is equal to plus or minus half. However, k has to be greater than 0. Therefore k is equal to half. Got it. Okay. Calculate the y-intercept of the f graph. So how are we going to calculate the y-intercept of the f graph? Okay, we can do it in one of two ways, right? We can say that 6.3, we can say that from the parent function has a y-intercept of 0 and 1. But we shifted the function 4 units down. So the y-intercept should be given by x being 0 and it'll be 1 minus 4. So it should be given by 1 and minus 3. Or alternatively, what I could do is I could say that the y-intercept is a point where x is equal to 0. So therefore f of x, or rather f of 0 is equal to half to the power of 0 minus 4. Any number raised to the power of 0 is 1, and so therefore I get the value of 3. So therefore the y-intercept should be 0 and 3. Sorry, minus 3, right? Minus 3. On the same set of axes, sketch the graph of G and F, showing all the intercepts and with the axis and okay. So what we can do now is we can do the following, right? Okay, so what we know is we know that the turning point of the parabola is at minus 5, 0 and minus 5. We know that the x-intercepts is minus 2 and 0 and 2 and 0. Right? Remember that these distances has to be the same. And so I can draw my parabola in. Right, that's the parabola. Put your arrows. And for the exponential function, we know that the exponential function has an asymptote that lies at minus 4. It lies at minus 4. So I'll call this y is equal to minus 4. I know that the intercept is at minus 3. And I know the function passes through this point here. Now again, let's go through our rules. We know that a is greater than 0, but b is between 0 and between 1. So therefore, we know that we're drawing a function that lies above the asymptote, but is decreasing. So how do I draw a decreasing function above the asymptote? It'll be either one of these two options. This is the decreasing function. So therefore, I need to draw a decreasing function that passes through that has an x-intercept of minus 2 and 0, that has a y-intercept of 0 and minus 3, and just approaches the asymptote, and has an asymptote of y and y is equal to minus 4. And so what we can do now is we can label our function. So we know that the g function is the parabola. We know that the f function is the exponential function. Don't forget to add the arrowheads to the axes. Okay, let me just move it. Why there's 2 here, right? And so that's basically how we solve the problem. So remember, you want to include both of the axes you have. So you have your axes x and y axes. You can also label the asymptote. You have to label your asymptote. So there we have our asymptote labeled. Your axes, you labeled your graph, and so that's about it. So that's how we solve this problem.